Let's look at the final questions on our semester exam review. This first question, question number 21, is asking us to match polar equations with their graphs. And so we have the different types of equations that we looked at in class with the different graphs. We're just going to try to remember some of the features of these polar graphs and how they're related to the equation. Let's start with these first two equations here. I notice in both of these I have an amplitude of 3 and I have a vertical shift of 2. One of them is a sine and one is a cosine. So what I'm going to do is sketch a quick rectangular graph of this relationship. We have a vertical shift of 2, so that means my midline is going to move up to 2. There's the middle of my graph. Amplitude is 3, so that means I'm going to go as high as 5 and as low as -1. And pi and 2 pi, with the pi over 2 and 3 pi over 2 marked there. I'm going to graph the sine equation. So sine starts in the middle. It's going to go to its maximum, back to the middle, down to the minimum, back to the middle. So there is our sine graph. Now what's important about this graph is that if you'll notice it crosses the x-axis twice. And what that means is that my r value, my radius, is going to be equal to 0 twice, which means my polar graph should pass through the pole or through the 0 origin. It should pass through there twice. Also in between these two zeros, my graph up here goes negative. And what that means is that my polar graph is also going to go negative. So for example, between pi and 3 pi over 2, my graph should be in quadrant 3, and it will be in quadrant 3 for this part here, but then once it goes negative, we're going to be graphing in quadrant 1. And then the same is going to happen here for quadrant 4 angles from 3 pi over 2 to 2 pi. I'm going to start out where the graph is negative, which means it's going to start out in quadrant 2, and then we're going to finish out this positive part actually in quadrant 4 where the angles are. So what happens here, I'll just say this first one is going to match up with C, and what happens is that as we go around, this graph is going to start right out here at 2, which is where my graph started. It's going to go up to 5, which is as high as we went here for quadrant 1. At the end of quadrant 2, we're back to 2. And then notice right here, we're in quadrant 3, so that matches up with the positive part, but then it goes negative. So we go over into quadrant 1, passing through the pole. And then the graph comes back through quadrant 2 for those quadrant 4 angles, and then finishes out in quadrant 4. So this little inside loop, it corresponds to where my rectangular graph is negative. And so that means that C goes with this first function. The reason that we went negative is because my vertical shift is smaller than my amplitude, and so the amplitude pushed us down into the negative r values. The other graph that has that little inside loop is graph E. And notice that graph C, it was centered up on the y-axis. Graph E is centered up here on the x-axis. And so this is the one that's going to go with cosine. And C goes with sine. Now in the next two equations, notice that the amplitude is equal to the vertical shift. They're the same. So again, I'm going to sketch a quick graph. Vertical shift of 2. Amplitude of 2, which means I'm going to go up to 4 and only as low as 0. And so my sine graph is going to look like this. What happens this time is that we only touch the x-axis in that one place right there, which means that my polar graph is only going to touch the pole one time. It's not going to pass through it and come back like we did with that little inside loop. It's just going to touch it and then move on. And so this scenario corresponds to the two graphs G and L. G and L, because you can see we're just touching the pole right there and then continuing on with the graph. G is the one that's centered up on the y-axis, and so that's going to go with sine. L is the one centered up on the x-axis, and so that goes with cosine. All right, next up, 2 sine theta plus 3. So this time we have an amplitude of 2, but my vertical shift is bigger. My vertical shift is 3. So what happens with that graph, let's see. Vertical shift of 3. If my amplitude is 2, that means I'm going to go as high as 5 and as low as 1. And so sine is going to start right here in the middle. High, middle, low, middle. So if you notice, this graph never touches the x-axis at all. That means that r is never going to be 0. And so this is going to correspond to graphs A and H. Those never touch the pole. Their radius is never 0. So A is centered up on the y-axis. That's the one that goes with sine. And H is centered up on the x-axis. That goes with cosine. All right, so now we're left with these flower graphs. And there's a couple things to remember when you're trying to match equations with a flower. First of all, the way that we know from the equation that we're going to be getting the flowers is because of the B value with the theta, the 2 theta and 3 theta and 4 theta. Those are the types of equations that result in flowers because we have a period change, and so it makes the curves happen much faster and we end up with flower graphs. If the B value is even, like these first 2 equations where the B value is 2 or these where the B value is 4, the number of petals is going to be 2 times B. So for these first 2 equations, we should be expecting 4 petals, and for the last 2, we should be expecting 8. 4 times 2. Now for the odd B, where we have 3, that's going to equal the number of petals that we can see. What happens with the odd value, there actually are 6 petals, but they end up graphing on top of each other, and so it looks like there's only 3. So let's do those 3 petal flowers first. I can see D and K both have 3 petals. D is centered up on the x-axis and K is centered up on the y. So that means D is going to go with the cosine. Whoops, that's the wrong one. D is going to go with the cosine and K is going to go with the sine. So now let's look at our 2 4-petal graphs. The 4-petal graphs are F and J. And with these even numbered petals, if the petals are centered up on the axes, like this one is, that's going to be the cosine graph. Notice that the J graph is not centered on the axes. That one's going to be sine. So the F goes with cosine and J goes with sine. And last up are our 2 flowers that have 8 petals. The I graph here, it's the one that's centered on the axis, so that's going to go with cosine. And then the B graph, it's not centered on the axes. That one goes with sine. All right, let's move on to our next question, which is a parametric equations question. And we've got a car on a highway. Its path is given by these 2 parametric equations, distance measured in miles and time in minutes. And then we have a train who's traveling at the same time, and the train has 2 different equations. First, we want to determine the coordinates of the intersection, and then we want to figure out at what time each one arrives at that point. Now, in order to find an intersection point, what we really need are the y equals equations where we get this relationship where y is in terms of x. Basically, or in other words, we want to eliminate the parameter, the variable t. So I'm going to start with the car equations. And the way that we're going to eliminate t is really what we want to do is combine these 2 equations together. And so I can have one equation that just has x and y. So I'm going to start out with this x is equal to 20t minus 15, and I'm going to solve for t. So x plus 15 is equal to 20t, and then I'm going to divide by 20, and so I get t equals x plus 15 over 20. Now what I can do is take this expression and substitute it for t in the y equation. So y is equal to 4t plus 30, and in place of the t, I'm going to put this expression, x plus 15 over 20 plus 30. So now I have a function that has y and it has x and there's no t's, and so this is something that I can graph on my calculator. We don't have to simplify because we can use a calculator here, and so we can just type it into the calculator in this form. Now I'm going to do the same thing for the train. For the train, we have x is equal to 2t plus 3. So 2t is equal to x minus 3, and t equals x minus 3 over 2. And now I'm going to substitute that into the y equation. Y is equal to 10t, so y equals 10 times x minus 3 over 2. And again, no need to simplify. We can type it into the calculator and graph it in that form. If we do graph both of those, we can find the intersection point, and that's going to be at 10:35. So that's our first question. We found the intersection. The second question asks us to figure out at what time each one arrives at that point. So I'm going to start with the car. If the car is arriving at that point, if I'm looking for a time value, I've got to use the parametric equations, and so I have x equals 20t minus 15. I want to know what value of t gives me an x coordinate of 10, because that would be the time when the car gets to the x coordinate of 10. So I'm going to change x to 10, 20t minus 15. I'm going to add 15 to the other side, and then divide by 20. And so for the car, t is equal to 5/4 minutes, or 1.25, either way. Now we could do the y equation also and set it equal to 35. We would end up with the same answer because the car is going to arrive at both coordinates at the same time. So really you just need to do one coordinate. So now I'm going to do the same thing for the train. Our train, this time I'll use the y equation. Y is equal to 10t. I want my y to be 35. So 35 equal to 10t, and t equals 35 over 10. So t is equal to 7/2 or 3.5 minutes. So they both get to the point, but at different times, and so there's no collision here, just an intersection of paths. All right, last question, and this was the question left off the original review. Hopefully you have this. We need to be able to convert rectangular coordinates into polar coordinates. So here on A, I've got -4 square root of 3, 4, and I want to convert that to an r and a theta. First thing I'm going to do is just plot this point on a coordinate plane. My x is negative and my y is positive, so that means I'm going to be in quadrant 2. So I'm going to draw a triangle in quadrant 2. My x side is -4 square root of 3. My y side is 4. So I'm looking for this length here. That's going to be my r, or my radius, and then this angle is going to be theta. Let's start by finding r. To do that, we're just going to use Pythagorean theorem. R squared is equal to -4 square root of 3 squared. Make sure that you use parentheses there. If you forget parentheses on your calculator, then the squared is not going to square that negative, and you're going to end up with the wrong value. You've got to use parentheses. Plus 4 squared, and that's going to give you 64. And so that means that r is equal to 8. Now for theta, we can use an inverse trig function. I'm going to use inverse tangent, and I'm going to say that theta 1, because this isn't really the theta that we need, theta 1 is going to be equal to the inverse tangent of 4 over negative 4 square root of 3. And if you put that in your calculator, it's going to give you negative 30 degrees. All right, now negative 30 degrees, that's obviously not the angle that I'm looking for. That 30 degrees is really my reference angle here inside the triangle. 30 degrees, that's this angle right here. So to find the one that I'm looking for, the actual theta that I need, we're going to do 180 minus 30 degrees, and I get theta equal to 150 degrees. So the coordinates of my point here are 8, 150 degrees. All right, let's try this last one. I've got negative 5 square root of 2, negative 5 square root of 2. With both coordinates being negative, I know that this is going to be in the third quadrant. So I'm going to draw a third quadrant triangle. Negative 5 square root of 2, negative 5 square root of 2. And again, we need to find r, which is going to be this distance here, and then theta, which is the angle all the way around to that terminal side. So let's start with r. Again, Pythagorean theorem. R squared is going to be equal to negative 5 square root of 2 squared plus negative 5 square root of 2 squared. And so r squared is equal to 100, which gives me an r value of 10. So my r length is 10. We also need to find theta. Now one thing that I'm noticing here is that both sides have the same value. So theta 1 is going to be the inverse tangent of negative 5 square root of 2 over negative 5 square root of 2, which is actually the inverse tangent of 1. And so hopefully we remember from our unit circle that means that our theta 1, our reference angle, is 45 degrees. Or maybe recognize that since the two sides of the triangle are the same, that the angle would have to be 45 degrees. Either way, my reference is 45 degrees. That's the angle in here. I'm looking for the angle all the way around from standard position. And so to find that, this time we're going to do 180 plus 45 to give me that third quadrant angle. And so theta is 225 degrees. And so my coordinates for this point in polar would be 10, 225.